Hello everyone. Today we're going to be looking at center of gravity and moment of inertia because we need these for Newton's second law of rotational motion. Center of gravity is very similar to what we discussed in a previous chapter on center of mass. Center of gravity is the position on a rigid body, and we've been looking at rigid bodies, at which the weight is considered to act to produce a torque. In other words, the line of the weight does not go through the axis of rotation, and it will produce a torque. Now, how do you determine the center of gravity? It's also very similar to center of mass. You look at every particle in your object and its distance from the axis of rotation, which is a radial distance, by the way. So you take the weight of each particle, multiply by its position from the radius of rotation, or from the axis of rotation. So however many particles you have, you add up all those weights times radial positions, and you get the total weight times position, but that's also the sum of the torques. Now, you're thinking, well, how is that the sum of the torques? Well, if you'll think about it a moment, the weight of each particle is a force, and you're multiplying by a radial distance from the axis of rotation. That would make that a lever arm. So you're basically looking at the torque that each particle is producing. So if you add all those up, you're basically summing the torques for all the particles in the object. Then you simply divide by the total weight, all the weights added together. And that will give you the position of the center of gravity. As long as the axis of rotation goes through the center of gravity, no torque is produced. But if the axis of rotation is not through the center of gravity, then the center of gravity will produce a torque around that axis of rotation. And hopefully, if I can do another video, I'll show you some examples. Now, going on, for any homogeneous, symmetrically shaped rigid object, we typically take the center of gravity to lie at the geometric center of the object itself. So if you have a long, thin rod, maybe like a meter stick, the center of gravity would be located at the linear center. And for a meter stick, it would be the 50 centimeter mark. For a cube, it'd be right in the center of the cube. Same for a cylinder. Now, some regular shapes might actually be hollow. And yes, the center of gravity can be located in the empty space in the middle. So in this case, you have a donut shape. And here the center of gravity would be located in the middle of the hole. It may be an empty space, but that is where the center of gravity is located. So if you had an object that was like this, that was rotating, say, about one edge, it was rotating around this point, then the center of gravity is producing a torque. Okay? Now, let's take a look at how we can use the center of gravity in both static rotational equilibrium and, more importantly, what we're looking at today, Newton's second law and rotational motion. In other words, we're going to be looking at non-equilibrium situations. The object is speeding up or slowing down. Knowing where to locate the axis of rotation, the center of gravity of different shaped objects is going to be important here. Now, Newton's second law for linear motion, or translational motion, as some books call it, we know that the net force acting on the object, which is the sum of any forces acting on it, is the mass of the object times its linear or translational acceleration. This is Newton's second law for linear motion. But we're not moving in a line, we're moving in a circle. We're rotating around an axis. In this case, we talk about the net torque, or sum of the torques that are acting on the object to make it rotate. In this case, the sum of the torques, or net torque, will produce an angular acceleration. So as you can see, there's an analogy here. Net force is analogous to net torque, and translational or linear acceleration is analogous to angular acceleration. But what about this right here? In Newton's second law, here we use the mass of the object. But in angular dynamics or rotational dynamics, we don't use the mass. We use a quantity called moment of inertia, or inertial mass. And if you'll turn the page, we'll see what that looks like. Okay, so now, moment of inertia is designated with a capital I and measured in units of kilogram meter squared. So if we stick that in right here, we get Newton's second law for rotational dynamics is the net torque, or sum of the torques acting on the mass, is the moment of inertia of that mass times the angular acceleration. Now, moment of inertia of various objects is different depending on their shape. We use calculus to determine the moment of inertia of an object. And for different shapes, it always turns out to be some ratio or fraction of the quantity mr squared. Okay? So, if you look on page 243, since we have a new textbook, it is now a new page number. But on page 243 of your text, they give you various geometric solids and their moments of inertia that have already been calculated into a formula form. So it says right here that there are two typos. That's in the old book. So this particular sentence does not apply to you guys because the new book doesn't have those typos. All right? However, it is true that for a thin rod with an axis at the center, in other words, let me show you. If you have a thin rod with an axis at the center that's rotating around that axis, the moment of inertia is 1/12 mass of the rod times its length squared. Now, I did not have in my word processor a 1/12, so I put a half there, and we're going to put a 1 in front of the 2 to make it 1/12, okay? However, there is a difference when the rod, instead of rotating at a point through the center, is rotating around one of the ends so that the entire end goes around. The entire length of the rod is now the radius of the circle instead of half of the length of the rod being the radius of the circle. In this case, the moment of inertia is 1/3 ml squared. And this, again, these two expressions come from calculus. However, we can derive a similar formula simply to show that, yes, the moments of inertia for these two situations are different even though the rods are the same. So let's take a look. If we put a steel ball on each end of the thin rod, if the axis of rotation goes through one end, okay, then for a mass, the tangential force acting on the mass to make it go around the circle, this mass doesn't have any bearing because it's not going around in the circle like this one is. So we only have to have one m when we substitute our translational Newton's second law. The lever arm for this mass would be the length of the thin rod. So that's the radius. If we substitute in our angular transformation between translational acceleration and angular acceleration. I'm just going to take r alpha and plug in for the translational. We get mr squared times alpha. Now, that means the moment of inertia is proportionate to one factor of ml squared from this formula. Now, in reality, it's 1/3 ml squared, but we're just looking at an example. We're not going to use calculus. We're just looking at this example to see how the two situations are definitely different. So now, if we change the axis of rotation to the center of the mass, here's what happens. The radius of each mass becomes 1/2 the length of the rod. And when we substitute in Newton's second law for the translational force, we have to put the 2m in, not a single m, because both of these are moving around the circle now. Collect our terms. But remember that in this case, the r is 1/2 L, not L. So we end up with 1/2 L quantity squared right here. Well, 1/2 is 1/4. 2 times 1/4 is 1/2. And then you have m L squared alpha. So now look and compare. For the two different locations of the axis of rotation, it is quite clear that the moments of inertia are different. Okay? That's as far as we're going to go today. I would like you to do your little activities with the videos, watching Billy, Bobby, and Bo. Okay? Work on those for today. And tomorrow I'll have some more notes up for you and an assignment that you can work on. Okay? Talk to you then.